Good afternoon, everyone. As per our meeting last week, you requested me discuss a little bit more about naming chemical formulas and writing information about balancing chemical equations and talking about word equations and skeleton equations. So let's go. So recall that a chemical formula is a combination of symbols and subscripts that represent the ratio of elements in a compound. And as you work with your periodic table, remember that the symbols for the elements from the periodic table are used to indicate which atoms or ions are in the compound. And the subscripts, or small numbers, are used to show how many atoms or ions of each element combine to form the compound. Now, you might recall the very familiar and most famous example that's always used, where we have sodium chloride. So our NaCl. Now with sodium chloride, remember that the sodium is the metal that's found over here in group 1, and chlorine, Cl, is the nonmetal found in group 17. When we look at their charges, or the ions that form the compound, remember that the ion for sodium in NaCl, there's only one sodium ion, right? So there's an Na+, and there is a Cl-. And when these two come together, that's where we get that total compound of NaCl to name it as sodium chloride. And the first element in this compound is the positive cation. The second ion is the negative anion, which is the chlorine, which we change the ending to "ide." Now, when you are writing formula and when you are naming, remember that we are looking at ionic versus covalent compounds. And then we can put these into reactions. We can then talk about the types of reactions and write down the equations and balance, so we know what's happening and how many of each thing we have on the left and the right-hand side of the equation. So take a look at these steps that I've written for you, and then we're going to do some examples with naming and writing. Now, when you have basic ionic elements from the periodic table, right, again, you're going to pay attention to what do you have over on the left-hand side versus what you have over on the right-hand side, right? It always works to color code your periodic table. So remember the periodic table activity I gave you where you were doing some coloring for yourself, right? Or you can always visit ptable.com, where that will also give you a color coding of what is the metals, the nonmetals, the transition elements, and so forth, as well as the metalloids, and where can you find the noble gases. Everything over to this side of the periodic table, these are all your metals, right? Except for hydrogen. This is a gas. Everything over on this side is a nonmetal, right? So you have all of your halogens and so forth and your noble gases. So this will become helpful when you are naming an ionic compound and putting together whether something has a positive charge versus a negative charge. Another handy tool that you do have at your disposal is from your Google Classroom, right? And it is your periodic table of ions. So this tool right here. Again, what you will notice is that you have all of your cations over here on the left-hand side of your periodic table, and you have all of your anions listed on the right-hand side of your periodic table, except for your noble gases, they do not have a charge. And this will help you put together and distinguish between what are the subscripts associated with certain elements within the compound themselves. So let's take a look at the rules. So if you are looking at writing certain formula for ionic compounds, remember that the metal ion is always positive and is written first. So we always write the name as the full name, what shows on the periodic table. Then the next step is that the non-metal ion is negative and is written second. Likewise, what we want to do is we want to also change the ending. So when you do end up changing the ending, What will happen there is that you will change the ending to IDE, IDE. The third step is that the total positive charge in the formula must be balanced by the total negative charge. And once the charge is balanced, write the chemical formula using subscripts if needed. So where we're saying that this part here, if needed, that means that you're going to take a look at using what we call the crossover rule. And I will demonstrate that in a few examples. With our sodium chloride, we had here a 1-to-1 ratio, right? Because we had a +1 and a -1 charge. So therefore, when we do the cross, what you end up having is an Na1 and a Cl1 at the bottom. So the ones are omitted here. So therefore, all we end up writing is NaCl. And we don't end up with little ones as a subscript in this case. So that's what number 4 means. So once the charge is balanced, write the chemical formula using subscripts. So in this case, we know, and all chemists know, that there are little ones beside the sodium and the chlorine within this compound, but the ones are just over redundant. So that's why we don't write them in. But you'll notice for the other examples that sometimes there's a little 2 over there, or a little 4, or a little 3, or something like that. So in that case, the subscripts become important. Now, when writing formula for other ionic species, there are 2 special cases, as you've seen in some of the tutorials. So for transition metals and for polyatomic ions, that's where we're going to see the use of the Roman numerals for transition metals. And we are going to see groups of atoms that have a collective charge, where we have the polyatomic ions. And again, this periodic table that I just showed you is going to be helpful. So where you see this table above, right, this polyatomic ion table, this lists everything that you have with more than one atom and a collective charge. So you have something like acetate, for example, with a total -1 charge, or if you're looking at, let's say, cyanide again, Cn-, or the dichromate ion, the Cr2O7 with a -2. So all of these things listed above the periodic table of ions have more atoms with a collective charge. So they travel together with that charge when they create a compound. So I'll show you how to name and write those in a few minutes. So let's take a look at some simple ionic compounds below. All right, so we just briefly talked about NaCl. That was our sodium chloride. So we'll just write that down again, right? Again, remember that with your sodium and your chlorine, right, you're going to take a look at splitting these up into ions. So that's +1. Cl is -1. Right, here we have the metal. Oops, sorry about that. Let me just change my color for a moment to make this a little bit easier for you to see. So sodium is the metal, the chlorine is our nonmetal, and when we put these names together, where am I getting this information from? Remember, always consult your periodic table for the information. The metal keeps its own name, so we just write down sodium. This is chlorine, but you will change the ending to chloride. So the name of this ionic compound is sodium chloride. Now let's say you wanted to put together calcium and fluorine. The first step is you need to go to your periodic table and identify the chemical symbol for both of these. Right? So you could work with the periodic table of ions that I've provided you, or you could simply go back to the image above and look for calcium and look for fluorine. So let's say you use the table I gave you. Since that will be easier, let's work with coarse materials. Right? Calcium's over here in group 2. So it's Ca2+. So you'll write that down. And you're looking for fluorine. Fluorine is fluoride. You'll notice the ending has changed. Likewise, you're going to write down F-. So the F- is a -1. Hopefully you can remember that. Let's write that down. Okay, so we're going to write that here. Right? Remember, step 1 is to write down the metal ion. Remember, the metal ion here is the calcium. So we're going to write down Ca2+. So this is our metal. And the fluorine is -1. This is the non-metal. Okay, and we have both of these here, right? So we've written them both with the ionic charges above each symbol based on the number of electrons gained or lost to both of these to become an ion, right? So remember from the previous lessons that we have Ca2+, so from group 2, we know that this is a positive cation of calcium because it has lost 2 electrons, whereas our fluorine, our F- or F-1 from group 17 shows us that this is an anion because it needs to gain 1 more electron to form the stable octet and be balanced, right? It wants that outermost valence level to have that 8 electrons so it is stable, right? When we draw those Bohr-Rutherford models to represent the ion. Now, what we want to do is we want to take a look at balancing the charges. So if you're thinking about how does step 3 and step 4 come about, figure out the crossover rule, right? We know that we can just jump ahead, and we know that we're going to cross the 1 to the bottom and the 2 to the bottom to get our compound. But if we want to check the charges, just like one of the videos Tyler was explaining, right? You can do so by looking at adding more positive or negative ions as required until the charge is balanced. So for example, you know over here that calcium is a 2+, right? Whereas on this side, we only have 1 fluorine atom. So remember your integers, right? So if you have something that's more positive on this side, how are you going to get it to 0? Well, you need another F-, right? So you're going to have a -2 and a +2. Remember that 2+ plus 2- is going to give you 0. That's your total charge. So that's what step 3 and step 4 are looking at. So this is why the crossover rule works. So this is just a proof, if you are wondering. So therefore, what ends up happening is that you can write your formula using the subscripts to indicate the number of ions of each type. So this just proves the crossover rule works. So therefore, we can cross our charges and we end up with a compound that looks like this. And in naming it, we have compound calcium fluoride. And there we go. We'll do the same thing here for the aluminum sulfur. Right? You will consult your periodic table again. Right? Here's aluminum. It has a 3+ charge. You're going to also look for the non-metal. Remember, they're found over here. There's your sulfur, which is sulfide, S2-. So we're going to write these two things down once more. Okay. And then follow the steps. So if you want to prove what's happening in terms of the charges, you can do so for steps 3 and 4, or simply follow the crossover method, right? Bring everything closer together and cross like so. So what you should end up with is the compound aluminum sulfate. And there you go. So once you do a lot more practice, these should become straightforward. So these are our basic ionic compounds. Now moving over to transition metals with Roman numerals, we have two examples here for you. So we have Fe2O3 and copper 2 oxide. Naming these two compounds is exactly the same. Again, you are going to look at your compound, identify your metals and your nonmetals from your periodic table, right? Just look for the chemical symbols, right? Look, what is Fe? What is O? The O might be more obvious, right? O is oxygen. And you might have to search a little bit to figure out what the Fe is. So if we go back to our periodic table, right, you're going to look here and search for Fe. So Fe is right here. What you're going to notice is that there's two charges for the iron. There's an iron 3 plus and an iron 2 plus. So which one are you supposed to use? You're also going to look for the O. So we have oxygen, oxide, and that's an O2 minus. So let's go back and write these things down. So we know oxygen is O2 minus, and this is an oxide. And we know that this iron can either be iron 2, which is Fe 2 plus, or it could be iron 3, which is Fe 3 plus. Now what's going to help you figure that out is by looking at the number that you have in terms of crossing over. So the subscript value. Remember that when you work backwards from the names and the drawing of the compounds, right, just like how we were doing previously, right, these subscripts come from crossing over. So we already know that oxygen can only exist as O2 minus. And now you're working with either an Fe3 plus or an Fe2 plus. But oxygen can only have been one of these combinations. So which one of your irons could it have been to give you a crossing over of the following, right? And remember as well from step 3 that your charges have to cancel out, right? To be neutral or be zero. So it makes more sense that taking a look at your diagram here, right, or of your subscripts and whichever iron it could have been, it's probably iron 3. So the name of this compound is the iron 3 oxide, right? Or you could always review the video by Tyler and see how to come about figuring out the charges on this molecule, right? Because for every amount of oxygen, you do want to have 3 oxygens corresponding to the 2 irons to cancel out the charges, right? Because remember that, oops, keep zooming in and out here, that you want to have those collective charges on both sides, right? So what do I mean by that? So if you have Fe3 plus and an Fe3 plus, right? 3 plus 3 is a 6 plus charge, right? So for every oxygen that you add, you need 3 oxygens with 6 minus, 2 irons with 6 plus to give you 0, right? So they cancel out, and so the compound is neutral. Now we have copper 2 oxide, same idea. This time I gave you the name of your compound here. You're going to go to your periodic table. Remember that this portion of the transition element already tells you which copper you have. Oxide is oxygen. And we don't have to consult the periodic table this time because you already have oxide up here. So this is O2 minus. So you already have one part of your compound. Copper 2, hitting up our periodic table again. Okay, let's see, where could copper be? It's in one of the areas over here. Looks like it's element 29, copper 2, match your Roman numerals, it's Cu2+. So let's go back and write that down. And all we're going to do is cross the charges and do the crossover rule. But what you're going to notice is there's these two little 2's at the bottom, right? Remember how we had something earlier like this with Na1Cl1? What you can do is you can reduce the charges and get rid of these numbers, right? If you do 2 divided by 2, what ends up happening is that this compound gets written as CuO. So this is actually the chemical formula of copper 2 oxide. So here in this case, remember to reduce the subscripts. So maybe you came across that in one of your homework questions. Lastly, looking at the polyatomic ions, we have, again, groups of atoms with a collective charge. We've got sodium sulfate for you. We have a CaOH with a 2 outside the brackets, and a lead 2 nitrate. Same idea. Again, we have metals combining with something with a negative charge. Consult that periodic table. Sodium is Na, and you might be wondering to yourself, what is this sulfate thing, right? Go to the periodic table again, right? This periodic table is going to become your friend, your best buddy by the end of this course. So now you're going to deal with this table above, right? And you are going to be looking for the sulfate. So sulfate is right here, SO42 minus. So write that down. That means that this whole thing has a charge of 2 minus. And you're just going to cross the charges. This becomes NaSO4, and that 2 goes in between the Na and the SO4. And there's not really a 1 out here, so you can just rewrite this as this. There you have it. Same thing for the lead 2 nitrate. The lead 2 stays together. The nitrate is the polyatomic portion. The lead 2 is your transition metal. So same idea, back to the periodic table, and then we'll come back to this one in a minute. So periodic table, we're looking for lead 2, and we're looking for the nitrate. So the nitrate's up here under N, it's nice and organized for us. Nitrate, ATE, is this one right here, the NO3 minus, and the lead 2, lead number 82, lead 2 is right here, Pb2 plus, and we have an NO3 minus. So that one and that one. So again, crossing over the charges. So this is going to cross over there. That one is going to cross over to the bottom. So what do we end up with? We get a Pb with a 1. We get an NO3. Put this in a bracket and put a 2 on the outside so it's less confusing for you. And then you can rewrite it neatly. Pb NO3 with a 2 on the outside. Your polyatomic ion is within the brackets. So this is our lead 2 nitrate. And then for our last one here, the Ca and the OH and the 2 in the inside, right? What is Ca? We just previously worked with that. Right? Ca is calcium. Right? Remember, calcium is a 2 plus cation. And you might be wondering, what is this OH thing? Back to the periodic table. This is one of your polyatomic ions. This time, let's take a look here. OH, OH, OH. OH. Right here. It's this thing, hydroxide. So it's an OH minus. So we're going to write that one down. Okay. So it exists as hydroxide. OH minus. And if we take a look at how it's written, right, it makes sense to the crossover rule that it had a -1 charge. The calcium had a +2. So when it was crossed over, we can see the OH is in brackets with that 2 on the outside. So the name of this polyatomic ion is calcium hydroxide. And then last but not least, we just need to mention the covalent compounds, but I'll show you how to name that in the next video. So hopefully this one was informative. Again, take a look at the examples, do the practice questions that are posted online, watch the other videos by Tyler, Mr. Anderson, and so on, Melissa Mirabel, and I will see you in the next video. Take care.